Geometry, lesson 90, composite transformations. This is like the, I don't know, probably the fifth lesson we've had on transformations. We had introduction to transformations, then we had a lesson on specific transformations, so we had a specific lesson on reflections, a specific lesson on translations, a specific lesson on rotations, and now we're back. Okay, so this is like the fifth lesson that we've had on this. Basically what this is the combination. If you notice it says composite transformation. So more than one transformation can be applied to a figure. A combination or transformation is called a composite transformation. If a figure is both translated 3 units to the right and rotated 90 degrees, for example, it has undergone a composite transformation. Any transformation, we can use any transformation as long as we have two or more. It's going to be considered a composite transformation. So we could have two translations, right? You translate something 3 units to the right, 4 units down, and then translate it 3 units to the left and 4 units up, right? That would be a composite transformation, okay? We could translate and then reflect. We could translate and then rotate. We could translate and then translate again. Right? We could reflect and then reflect again. We could reflect and reflect and reflect and reflect again. Right? It's any combination. So there's really no limit to the combinations that we could use to create composite transformations. Okay? Hopefully, let's move. Come on. Do your thing. Make sure we did. There we go. Composition of two isometries is an isometry. Now we do this every time that we come into this, specifically in transformations. I ask the question, what is an isometry? Can anybody tell me? What is an isometry? Same shape and size. So it is a transformation that maintains the size and shape of the figure. Very good, Mick. So we want to recall that translations, rotations, and reflections are all isometries. They maintain the size and shape. They may change the orientation. A composite transformation with two or more of these transformations will also be an isometry because, you know, so long as we're not applying a dilation to this, we're going to wind up with the same size and shape. Okay? There are a couple specific composite transformations that they do talk about. One of these is a glide reflection. Glide reflection simply means that we're going to translate it and then we're going to reflect it. So it's a composition of a translation and a reflection across a parallel line to the translation vector. Since a glide reflection combines translation and reflection, it is also an isometry because those two things are isometric. Seem pretty simple so far? You guys seem really excited. Okay. Two reflections across two parallel lines. This will be an important one to look at and remember. The composition of two reflections across two parallel lines is a translation. We'll say that again. If I reflect a figure, let's see, let's say I've got these two parallel lines here. We've got this green triangle. If I wanted to reflect it across to this red line right here, okay, it would look like that, correct? Yes? Okay. And then if I want to reflect it across this second red line, it would look like that. And that's, maybe if I slide down here a little bit, we'll fix this. Okay. I'm going to get something that looks roughly like that. Okay. So the reflection across two parallel lines ultimately ends up as a translation, because if I look, okay, does it maintain the orientation? Yes. Okay. So the reflection across two parallel lines essentially results in a translation. Okay. Further definition says if a figure is reflected twice, the end result is an image that represents a translation from the original pre-image. Okay. Two reflections across two intersecting lines. Okay, so if I've got two lines that cross, and I want to reflect across one line and then the other. The composition of two reflections across two intersecting lines is a rotation about the point of intersection. So, you know, not necessarily the origin, just where those two lines cross at. the angle of rotation is twice the angle formed by the intersecting lines. If a figure is reflected across the lines that intersect, it results in a rotation of the figure. We'll see this as we start to work out some questions. Okay? Let's see. Hopefully I even have that with me. And that's the end of that. So from here, we'll look at lesson 90. Okay, do you guys have this document? I know sometimes I forget to send things out. You guys got it. Perfect. Hopefully I'm not going in here blind. All right, let's look at this first one. Anne wants to create a design to decorate her geometry binder. She reflects part of the design across line P, then reflects the image across line N. Describe a single transformation that moves the part of the design from its starting position to its final position. All right, what did we say that the reflection across two intersecting lines would be? Rotation. Okay, so just like how we said the reflection of a figure across two parallel lines was translation, the reflection of a figure across two intersecting lines is rotation. Specifically in this case, notice that these two lines are 90 degrees, right? And we said that if we reflect across two intersecting lines, that the angle of rotation would be what in relation to the angle formed by those two intersecting lines? Was it 1/2 or was it twice? Twice. So here they intersect at 90 degrees. So how many degrees of rotation do we have from here to here? 2 degrees? 180 degrees. 90 times 2 equals 180 degrees of rotation. Now, and I believe they do ask for that. Describe a single transformation. So we have a rotation of 180 degrees about the origin. Okay? So we're going to go with A for that answer. Somebody check down at the bottom. Is that the correct answer? Yes? Okay, perfect. All right, let's come down here a little bit further. Okay? Copy each figure and draw two lines of reflection that produce an equivalent transformation of translation from triangle DEF to triangle D prime, E prime, F prime, and some of this is even cut off. So let's try to fix this. All right, what does this look like from EDF to E prime, D prime, F prime? What kind of transformation does it look like? Does it look like a translation, a reflection, or rotation? Somebody says reflection. So if I draw a single line here, it looks like it's been flipped. It looks like a translation, right? Okay, so it looks like a translation, but they tell me to draw two lines of reflection. Okay, so what kind of lines do they have to be for it to reflect across both those lines and for it to look like a translation? Parallel lines. Okay, so we can simply draw two parallel lines between them, okay, in order to get this. So we'll clear this out and we'll pick, out of this, okay, which one of these, now we're going to see parallel lines, okay, but which one of these looks like what it should be? A, right? B has parallel lines on the outside, we obviously can't reflect to get there. C has parallel lines on the outside. D still has those parallel lines. Okay, and I might go so far as to say that D might be a possibility. What does your answer key say down at the bottom? A is what it should be. I think it has more to do in this case with this dotted line that's right here, showing where we're going, right? We're going from D to M to D. Okay, I think that's the main problem with D, is this line comes across here. Okay, let's go down to question number 3. Okay, ABC has vertices at 3, 1, 4, 5, 2, 3. and you'll notice that all four of those pictures start out in the right position. Okay? We want to rotate this 90 degrees counterclockwise about the origin and then reflect it across the x-axis. So the first thing I want to talk about is counterclockwise 90-degree rotation. Now, if we go back to our notes, we probably have a rule for this, right? We have that somewhere? What's our rule whenever we want to have a counterclockwise rotation? I'll hit pause on the video while you look it up. So we're going to hit record here. Okay, page 511 in your geometry textbook. You should see about the middle of the page. If a point XY is rotated 90 degrees about the origin, and the assumption is always that it is going to be counterclockwise unless they tell me otherwise, then my mapping notation takes me from XY to negative YX. XY to negative YX. Okay? All right, so I can look at these coordinates and see that A prime should be negative 1, 3, right? This should be negative 5, 4, and this should be negative 3, 2, correct? All right, so I could look through here and see which one is going to map out at the right place. Negative 1, 3 looks good. Negative 5, 4, that looks good. Negative 3, 2, so far that looks good. All right, so our first rule is going back and actually using some of the things that we learned in previous lessons, correct? Now I want to reflect across the x-axis. All right, well, don't we have rules for how to move those coordinates across the x-axis? What ends up changing when I reflect something across the x-axis? Just the what value? The y value becomes opposite, right? So now I'm going from A to A prime to A double prime. So I want to use negative 1, 3. So we're going to keep negative 1, and 3 becomes negative. Okay? Over here, right? Negative 5, negative 4. Over here, negative 3, negative 2 is where A double prime, B double prime, C double prime should be. So let's look at our final position. Negative 1, negative 3. Okay? Negative 5, negative 4, negative 3, negative 2. So do we see why A works? Right? Not just trying to get there visually, but using the rules that we've learned from previous lessons, correct? Okay? So the two mapping notations that we're using there are, we're using this for rotation, we're going to use this for reflection across the x-axis. Okay? Now, if you wanted to skip the in-between, you could go ahead and apply both of those off the beginning, right? Right? So without having to even draw the picture, you know where you would wind up at. Okay, let's go on down. All right. Number 4, reflect triangle QRS across line M and then translate it along vector V. All right. The easiest way to do this is to look at each individual point, okay, and reflect it. All right. So if I'm going to reflect across, remember when we reflect across a line, what is the relationship of that point to the line of reflection? It should be what to it? I know it's a tough question to answer if you don't know where I'm going. What is the angle between S and S prime across line M? At what angle does, at what angle is the blue line to line M? 90 degrees. So what we're saying is that it has to maintain a perpendicularness. Perpendicularity? No, no, it's just they need to be perpendicular, okay? And they need to be the same distance across, which means line M should be the midpoint of my blue line, right? Hopefully, okay? All right, so I am drawing S prime. Can I get somebody to draw R prime? Let's see, who do I want to? Brady's got it? Awesome. And if it helps to draw the line across, you can do that just to help you estimate it out. Okay? All right, so we'll call that R prime. Okay, can I get somebody to do Q? Darian? Okay, good, thank you. All right, that's not too bad. All right, we got Q prime there. So if we finish this guy out, we should see something that looks roughly, right? We're just hand drawing it. If we really wanted to be specific about this, we'd want to get out graph paper, put things on a coordinate plane, figure out slopes, figure out distances, those types of things where we could do the math to be precise. Okay, so that was the reflection. The next thing that they want us to do is to translate it along vector v. So we want to be parallel with vector v as we move across. So I'll do kind of that part for us, so that we would move across parallel till we got something that maintained that basic shape. Okay, we would get S double prime, R double prime, Q double prime is my final location. So reflect and then reflect and then translate. This is what is called a glide reflection. Now, we could have, if they'd asked us to, we could have translated this along vector v on the same side of M and then reflected it across line M. We would have wound up in the same position. Okay, can we see that? Great. All right, let's see, question number 5. Reflect the figure below across line C, then reflect the image across line D in a diagram C is parallel to B. Miss Al, would you reflect point F across line C for me? Just point F. Okay, and I think I'm going to erase this. Can anybody tell me what might be wrong with that? It's not 90 degrees with what? It's got to be 90 degrees with line C. So let's try that again. 90 degrees with line C. All right, so this is line C right here. What we want, 90 degrees is going to be perpendicular. So what kind of line is perpendicular with a horizontal line?
Like this.
Okay, perpendicular is like this, right? All right, line C could very easily be that line, right?
Okay.
So let's imagine that this is line C. Point F would be right there, right? All right, which means F prime would be right there, correct? So let's apply that over here. Very good, right? Because essentially what we should have is a perpendicular line. The only thing that might be wrong about this is that our red dot might be too far away, right? Because if this is my line of reflection, we probably want that a little bit closer. All right, let's try that again. That's probably pretty close, right? Okay. All right, do you want to try G? That may be a little tougher. And the toughest thing about these is estimating the distances. So like if we look across here, right, we would want these two to be the same distance across. So the easiest way to make sure that this angle, this FG angle, is going to be maintained is to try to go the same distance. So what we might do is try to estimate that distance right here. Here, let's start over there. Okay, how long would you, estimate that line on down across? About right there. Yeah, and if we do this, right, we should see, okay, that line looks about right. Looks about the same. Okay, now we're going to do something else here. Austin, let's see if you can help me out. This is F prime and G prime. Okay, we want to take F prime and G prime and reflect them across line D. Can you do that for me? Okay, just do your best. If you have to, draw a line down across, you can. Okay, and we have kind of the same problem here that we had with F, is that this line from F to D needs to be the same distance from D across. So do you think that we went far enough, or do you think we need to go further? Probably need to go further. So let's erase from D there, if it will, okay, and try to take it the same distance across. Okay, because perpendicularly you were good, right? You just didn't go far enough.
So like further down this way?
Further down, yeah. About the same distance. That's pretty good. Okay, that'll work. And we would call this F double prime, right? Okay. Do you want to try G?
Sure.
Okay. Go ahead. I would just draw another line. Okay. Again, it needs to be the same distance from here to here. It needs to be the same distance across. Okay. Now, in the end, the question we want to ask ourselves, does this line look like this line? No. What's wrong? Do you think, because it looked like these two lines were running parallel with line D, right? So what I would say is that you went too far, right? So you got to find that. Oh, hold on. No, that's my fault. Okay. So when we get that same distance again, it's going to have that same slant, but again, if you look from here to here, right, it needs to be the same distance. Okay, it still looks a little weird. So this is what I'm going to do. I'm going to go through here, and I'm going to start over. Okay, so I'll take the pen. All right, see if. Because I think, one, F prime needed to be a little closer. As we look across, kind of tighten it a little bit. All right, does that look? Okay, and then here. I don't know. It's going to be a little tough without a ruler. If you had a ruler, would that be a lot easier to do? Yeah, because you could measure the distance from F to the line and then go the same distance across. You could measure the distance from G to line C and then go that same distance across. We would do that same thing from F prime to F double prime, from G prime to G double prime. Okay? Is that the last question in here? Okay. All right, so we'll stop there. But hopefully you guys get the concept behind this. Okay.